Welcome to Beyond the Brackets. Let's continue non-exact differential equations of type 4. This is the first question given. Let's call it as equation 1. Equation 1 is of the form m dx plus n dy is equal to 0, where coefficient of dx is m and coefficient of dy is n. To check the exactness, we differentiate m partially with respect to y. Differentiating xy cube gives 3xy square and differentiating y gives 1. Next, we differentiate n partially with respect to x. Here 2 is constant. Differentiation of x square y square gives 2xy square and differentiation of x will be 1. Since both the results are not equal, equation 1 is non-exact. Let's come back to the question. The first term xy cube is of degree 4 and the second term y is of degree 1. So this rules out the possibility of equation 1 being homogeneous or type 1. Next, for type 2, we observe that the entire term with dx is multiplied by y, but the term with dy is not multiplied by x. Hence, it's not type 2 either. Now we check for type 3 and type 4. Let's do a quick comparison. Subtracting the partial derivatives gives 3xy square minus 4xy square, which will be minus xy square, and 1 minus 2 will be minus 1. If we divide this with n, the expression becomes more complicated, but dividing with m leaves only y term. So this equation belongs to type 4. So equation 1 is non-exact and is of type 4. Substituting the values and taking y common in the denominator, the terms cancel out, leaving 1 by y, which we call g of y. The integrating factor for type 4 is given by e power integration of g of y dy. Since g of y is equal to 1 by y, its integration is log y, and e power log y simplifies to y. So the integrating factor is y. Multiplying equation 1 by the integrating factor, we get a new equation where the coefficient of dx is m1, that of dy is n1. This equation will always be exact. To verify, we differentiate m1 partially with respect to y. Differentiation of xy power 4 gives 4xy cube and of y square gives 2y. Next, differentiating n1 partially with respect to x. Differentiation of 2x square y cube gives 4xy cube and of 2xy gives 2y. Since both the results are equal, equation 2 is exact. The solution is given by integral m1, we take y as constant, plus integral n1, where we consider the terms free from x, is equal to c. For the first integral, substitute the values of m1 as it is. For the second integral, x-free terms are 2y power 5. Integrating the first integral with respect to x, y power 4 is constant. Integration of x will be x square by 2. Y square is constant. Integration of y square will be y square into x. For the second integral, integration of y power 5 will be y power 6 by 6. That completes problem 1. Now let's move to problem 2. Calling the given equation as equation 1, we observe that it is of the form m dx plus n dy is equal to 0, where m is the coefficient of dx and n is the coefficient of dy. To check for exactness, we differentiate m partially with respect to y. The derivative of y power 4 is 4y cube and of 2y is 2. Differentiating n partially with respect to x, derivative of xy cube is y cube and of minus 4x is minus 4. Since both the results are unequal, so equation 1 is not exact. It can be clearly seen that the equation is neither homogeneous, that is type 1, nor type 2. So we check whether it belongs to type 3 or type 4 by doing a quick calculation. Subtracting these two terms, we get 4y cube minus y cube will be 3y cube and 2 plus 4 will be 6. 3 is common in the numerator. We see that dividing by n makes the expression more complicated, whereas dividing by m cancels out terms, leaving only a function of y. Hence, the equation is of type 4. So, equation 1 is non-exact differential equation of type 4. Substituting the values, taking minus 3 common in the numerator and y in the denominator, the terms cancel out, leaving minus 3 by y, which we call g of y. Integrating factor is given by e power integration of g of y dy. Integration of 1 by y will be log y. Since a log b will be log b power a, so minus 3 log y will become log y power minus 3, so that is 1 by y cube. Multiplying equation 1 with integrating factor, a new equation is formed where coefficient of dx is taken as m1 and coefficient of dy is taken as n1. This equation will always be exact. To verify that, differentiate m1 partially with respect to y. Differentiation of y will be 1. 2 by y square will be minus 4 by y cube. Differentiating n1 partially with respect to x. Differentiation of x will be 1. 4x by y cube will be minus 4 by y cube. Clearly both are equal, so equation 2 is exact. Solution is given by integral m1 dx, we treat y as constant, plus integral n1 dy, we consider the terms free from x is equal to c. For the first integral, substitute the values of m1 as it is. For the second integral, we consider the terms that are free from x, that is 2y dy. Integrating the first integral with respect to x, integration of y will be xy. 2 by y square is constant, so that will be constant into x. Integrating the second integral with respect to y, integration of y will be y square by 2. Let's quickly move on to the last question. After calling this equation as 1, we observe that it's of the form m dx plus n dy equal to 0, where coefficient of dx is m and coefficient of dy is n. To verify the exactness, differentiate m partially with respect to y. The differentiation of 2xy square will be 4xy. For the second term, e power x is constant. Differentiation of y will be 1. Differentiating n partially with respect to x, differentiation of e power x will be e power x. Again, both of them are unequal, so equation 1 is non-exact. Looking at the question again, it's clear that equation 1 is neither type 1 nor type 2. To check whether it is type 3 or type 4, let's subtract these two terms. Get 4xy plus e power x plus e power x, which simplifies to 4xy plus 2 e power x. Now dividing this by n makes the expression more complicated, but dividing by m allows y to be taken common and the terms cancel out, leaving a term purely in y. Hence equation 1 is non-exact equation of type 4. Substituting the values and taking minus 2 common in the numerator and y in the denominator cancels out the terms. We are left with minus 2 by y, which will be called as g of y. Integrating factor is given by e power integration of g of y dy. Again, integration of 1 by y will be log y. Minus 2 log y can be written as log y power minus 2, that will be 1 by y square. Multiplying equation 1 with integrating factor, a new equation is formed, which will be called as equation 2, where coefficient of dx will be taken as m1 and coefficient of dy is taken as n1. To verify the exactness, differentiate m1 partially with respect to y. E power x will be constant. Differentiation of 1 by y will be minus 1 by y square. Differentiating n1 partially with respect to x, minus 1 by y square is constant. Differentiation of e power x is e power x. Again, both the values are equal, so equation 2 is exact. Solution is given by integral m1 dx considering y as constant plus integral n1 dy treating the terms free from x is equal to c. For the first integral, substitute the values of m1. For the second integral, we consider the terms that are free from x, so the second integral becomes 0. Integrating the first integral with respect to x, integration of 2x will be 2x square by 2. Integration of e power x by y, 1 by y is constant. Integration of e power x is e power x is equal to c. That completes today's topic. I have added 2 more problems with their answers for your practice.